So today's webinar is entitled Australia's Boundary Current Pathways to the Deep Ocean and will be provided by Dr Helen Phillips from the University of Tasmania. Helen is a Senior Research Fellow in the Physical Oceanography at the Institute of Marine and Antarctic Studies at the University of Tasmania. She is a contributor to the Earth Systems and Climate Change Hub Project 5.7, which is entitled Tracking Ocean Change, Ocean Observations and Models. Helen is a seagoing oceanographer with 20 years of experience in observing and interpreting ocean variability to understand the physical mechanisms at work and their impact on the climate system. So I'll pass over to you. Thanks, Helen.
Thanks, Sonia. So I thought I'd, start off with a little description of where I would like this talk to go. So I thought it would be useful to begin with a bit of a review of ocean surface currents, and then look at how the heat enters the ocean depths, and the meridional overturning circulation is one of the primary pathways. I'd like to talk a little bit about the Earth's energy imbalance, because that's changing how much heat is actually going into the deep ocean, and that comes down to too many greenhouse gases being put into the atmosphere, which are trapping too much heat. And we find that 93% of global warming is stored in the ocean. So then we'll look at how ocean heat uptake is not uniform around the planet. It varies by region. And then we'll come back to Australia's coastline and think about the special features of Australia's western and southern shores that help heat enter the deep ocean. So we'll look at downwelling along Western Australia and a pathway for southern ocean waters along a very long boundary current along the southern and western coastline. And then where to from here? All right, so to begin with a review of ocean surface currents, we really need to step back and look at where Earth fits in the climate system, or I should say the solar system. So here's a view of our planet Earth, little blue ball, third from the sun, and we very quickly get the sense that the sun is the primary reason that there's any life or motion on Earth at all. So the Earth's energy balance refers to the incoming solar radiation from the sun and the different pathways that radiation follows in the atmosphere. So if we look at I'll just change my pointer to something very visible. So at the top of the atmosphere, we have incoming solar radiation, and that works its way down through the atmosphere. Some of it's absorbed by the atmosphere, some's reflected by clouds and returned out to space, and some of it comes all the way through to the surface and is even reflected by the surface. And then on the outgoing side, the Earth is a warm body, and so it emits radiation, and some of that is absorbed by the atmosphere again, clouds and greenhouse gases, and some of it's reflected back to Earth. So there's a very convoluted pathway for energy in the climate system, and greenhouse gases are a key part of keeping the planet safe for us, keeping it warm, but if there are too many greenhouse gases, then too much heat is trapped on Earth. So, so this figure shows the effect of the sun's warming on ocean temperatures. So this is a long-term average of the global sea surface temperatures around the world, and there's a very strong gradient in temperature from below zero around the poles up to around 30 degrees and sometimes warmer in the tropics. So there's a very clear gradient, and this is due in part to the uneven heating by the sun. So this little schematic is intended to illustrate that uneven heating. So as the sun's rays hit Earth, they actually hit Earth at about 90-degree angle at the equator. But because of the spherical shape of the Earth, as we go northward or southward, the area over which the sun's rays hit the Earth expands, and so then the intensity of the light is reduced. So there's a lot less energy reaching the surface of the Earth at high latitudes compared to what's on the equator. And so this uneven heating contributes to the circulation of the atmosphere and the ocean, and that in conjunction with the rotation of the planet are key to setting up ocean currents. You'll notice here that the north-south gradients in temperature are actually not so horizontal when you come close to the continents. And this is actually the signature of the ocean currents and the wind circulation patterns that we'll see in a couple more slides. Or in fact, in one slide. So here's a map of the large-scale ocean currents. It's a very smooth and simplified view, and it's just intended to illustrate the really large-scale patterns that we have. So you can see in the southern hemisphere, there are subtropical gyres that are rotating in an anti-clockwise direction in the southern hemisphere, in the Indian, Pacific and Atlantic Oceans. And then the subtropical gyres in the northern hemisphere rotate in a clockwise direction. Then we have subpolar gyres in the North Pacific and North Atlantic. There are equatorial currents that are pretty much east-west. And we have the Antarctic circumpolar current. That's the only current that can flow all the way around the Earth because of the unbroken latitude. So there's no land that covers the latitudes spanned by Drake Passage. So that gives the Antarctic circumpolar current a really key place in our ocean circulation and climate system. So then we zoom into the currents around Australia, and there's an intricate network of currents. The orange arrows show the surface currents and the blue arrows show subsurface currents. And when we say surface, we probably mean in the upper 200 to 300 metres of ocean, and then subsurface below that. So you can see that on the east coast of Australia, we have the East Australia current moving southward and the Leeuwin current moving southward on the West Australian coastline, and an eastward flow across Bass Strait and south of Tasmania. And the subsurface currents actually flow in an anti-clockwise direction all the way around the coastline, southward and then westward across the bight, and then northward and offshore. So this pattern of currents will come back to as we look more into the vertical movement of heat in the ocean. So we're focused on the surface or I guess the horizontal circulation. So now let's move on to looking at how heat enters the deep ocean. That's my prompt. And so the meridional overturning circulation, also called the global conveyor belt and sometimes the thermohaline circulation, is the way that the ocean can communicate changes at the sea surface with the very deepest parts of the ocean. So in the figure, the reddish colour are the warm surface currents, and the blue are the deeper currents. And now we're talking around deeper than 1,000 metres depth. The purple ellipses show places where there are really strong interactions with the ocean and atmosphere. And so in the Labrador Sea and the Norwegian Sea, there's very strong cooling that turns surface waters into waters that are dense enough to sink quite deep and join this southward pathway. So that's the North Atlantic deep water flowing through the North and South Atlantic Oceans, and then finally joining the Antarctic circumpolar current in the Southern Ocean. Then there are also deep waters coming out of the Indian and Pacific Oceans, and they also merge with the North Atlantic deep water in the Southern Ocean. And those deep waters are gradually moving southward and upward as they go around the ACC. And these two purple ellipses in the Southern Ocean indicate where Antarctic bottom water is formed. These are the two primary locations in the Weddell and Ross Seas. And so here there's again strong interaction with the atmosphere that creates very dense surface waters that can sink down to the deepest depths in the ocean. So the next slide gives a bit of an illustration of how those deep waters rise up to the surface and how the ocean interacts with the atmosphere to create very dense waters. So there's a divergence in the deep waters as they approach the sea surface that's related to the wind circulation patterns. And some of those deep waters move southward onto the coast of Antarctica. And there's very strong cooling due to frozen winds coming off Antarctica. So there's ice formation. And the process of ice formation pushes salt out into the water that's left behind. So the ice only captures the fresh water and the salt is ejected into the water below. And the combination of very salty water with very cold temperatures leads to extremely dense waters that are in fact the densest in the entire ocean. So they sink down the slope of Antarctica and move northward as Antarctic bottom water. You can also see that some of the deep waters come to the surface but are directed northward because of the wind circulation, and they contribute to a shallower overturning cell. And primarily that's Antarctic intermediate water, which is very fresh, and subantarctic mode water, which is warmer and saltier. And those two move northward also to fill the ocean basins. So these are the primary means for water to enter the deep ocean. And here in 2 dimensions, you can see a bit more clearly the different layers. So now we're looking at a slice through the Antarctic Ocean and the Atlantic Ocean, with Antarctica on the left and the North Atlantic on the right. And so Antarctic bottom water is very clear, moving northward to fill the deepest parts of the ocean. North Atlantic deep water is not as dense and sits above it. And then we have the Antarctic intermediate water, subantarctic mode water pathways. And also in the subtropics, there's another type of water formation that leads to subtropical mode waters. So in all of these cases, properties at the ocean surface are being carried into the deep ocean that provides oxygen for the deep ocean. It also carries carbon dioxide and warming temperatures into the deep parts of the ocean. So I'll briefly touch on the Earth's energy imbalance, and that's beautifully illustrated in this figure from a recent paper, which talks about how the incoming solar radiation is now greater than the amount of radiation that's emitted back to space. So the outgoing radiation is smaller than the incoming radiation, and that's because the greenhouse gases in the atmosphere have been increasing in concentration due to human activities. And of the heat that's retained on Earth, about 3% is stored in the land and the atmosphere. 4% has gone into melting ice, sea ice and land ice and ice sheets, but 93% has been stored in the ocean. So the consequences of that increase in energy in the climate system is felt everywhere in all of the different parts of the climate system. So we know atmospheric temperatures are rising, the amount of moisture in the atmosphere is increasing because a warm atmosphere can hold more moisture than a cold atmosphere. That's leading to more extreme rainfall and storm events, flooding, some drought. There are melting snow and ice cover. And the ocean mass is increasing, so we have sea level rise because of the melting of ice, but also because warmer ocean expands and fills up more space, and so the amount of heat stored in the ocean is rising, as we've seen. And this is a bit of a time series of the change in ocean heat content since 1955, and it's broken up between the layer down to 700 metres on the left and below that 700 to 1,000 metres depth. So since the 50s, there's been an increase in the amount of heat stored in the ocean, and that's extending down to many depths. So this is a very average picture. It's taking all of the records in the entire ocean and turning them into one time series. This slide was to just give you a sense of why we use ocean heat content change as a metric for the Earth's energy change. And so on the vertical axis here, we have the amount of change in the energy of the Earth system, and on the bottom axis we've got surface temperature change on the left side and ocean heat content change on the right. And you can see that surface temperature changes are very noisy and don't give you a very tight relationship with the amount of change in energy of the Earth system, whereas ocean heat content change is an extremely good relationship, and if we can measure ocean heat content change, then we know very clearly what the change in the Earth's energy is. And a lot of this, well, most of this recent work, most of the recent measurements come from the Argo array, which has been global since 2005. But this just highlights the blind spot that we have, because Argo only covers down to 2,000 metres in the ocean, and it doesn't capture the polar regions or the boundary currents very well. So there's still a lot of ocean where we're not able to measure regularly the changes in heat content. So one point to make is that ocean heat uptake is not uniform, and by that I mean it varies regionally. So this is a figure from the 5th assessment report of the IPCC, which was published in 2009, showing the change in temperature since 1971 in the upper 700 metres. And you can see that there's warming pretty much everywhere, apart from a few places where there's some light blue areas. But the Southern Ocean is a place where there's quite strong warming, the Tasman Sea, and certainly the North Atlantic Ocean. And you can see, looking in the bottom panel, which shows how far that heat extends vertically, that the heat is penetrating very deeply. And we have a bit of an update from more recent times. So this shows the trends since 2005 from Argo observations, and it's prepared by a student, Sonia, who works in the Earth Systems and Climate Change Hub. And so the spatial map shows you the regions that have experienced the most rapid warming in this recent period, and here you see that the Indian Ocean and the Southern Oceans are taking up the lion's share. And looking at the depth section above, that heat is penetrating down to the limit of the Argo observations at 2,000 metres and very strongly in the Southern Ocean. Because things are changing so rapidly, the IPCC commissioned extra reports to look at the changes in the climate system, and the most recent report was looking at the ocean and cryosphere in a changing climate. And they've highlighted the increase in the speed of heat uptake. So since 1993, the rate of ocean warming has more than doubled. And it's focused in the Southern Ocean. So of that heat gain, 35 to 43% in the upper 2,000 metres has been taken up in the Southern Ocean since 1970, and that rate's increased since 2005. So that's also work being done by Earth Systems climate change people. So now to step back and look at our region and think about what's special about Australia's western and southern shores, and how do they contribute to this access of surface heating to the deep parts of the ocean. So this figure that we looked at before of annual mean global sea surface temperatures gives you a bit of a clue. You'll notice on the western sides of the South American and South African continents, we see cold waters moving northwards, and the other side of the basin has warm waters moving southwards. So the warm water moving southward are the western boundary currents, and Australia has one of those too. That's the East Australia current. But we also have a southward flow on the western side of of our nation, which is unusual. We don't have cool waters upwelling as the other ocean basins do. And the reason for that is because of this permeable landmass to the north. The Indonesian seas allow the very warm waters from the Western Pacific Ocean to pass through the Indonesian seas, where they receive a lot of rainfall and become very fresh, and then they move out into the Indian Ocean. So this sets up a gradient where we have very light, warm waters to the north and colder, fresher waters to the south, and that causes the southward movement of the Leeuwin current, but it also causes eastward currents to flow in towards Western Australia, and that prevents any upwelling from occurring. And so here's a bit of a zoom in of the Indonesian through flow. So it's the only low latitude connection between ocean basins. All the other connections are at high latitude. And there are very convoluted pathways for the Pacific Ocean waters to enter the Indonesian seas and then pass out into the Indian Ocean. So that's bringing warm, fresh waters to the tropical Indian Ocean, and it's creating this north-south gradient in density, which is also a pressure gradient to drive the Leeuwin current and the eastward currents. So then coming back to this figure, where we look in more detail at the currents around Australia, we've got the Indonesian through flow feeding the south equatorial current, and that's warm, fresh water. And in the subtropics, we have cooler and very salty water because there's a lot of evaporation that creates high salinities in that area. And so this density gradient from dense in the south to warm in the north drives an eastward flow, which is what we see in these orange surface currents moving in towards the coast of Western Australia and merging with the Leeuwin current. And I've mentioned already the 5,500 kilometre long boundary current, which was so named by Ken Ridgway and Scott Condy, thinking about the Leeuwin current moving down the west coast of Australia and then actually extending across the southern shelves of Australia and south to Tasmania, so 5,500 kilometres in total. So the eastward currents have now been mapped, working with new observations from satellite and models and Argo observations, and we find that there are eastward flows extending from Madagascar all the way across the southern Indian Ocean, and they merge with the Leeuwin current. And we also see some recirculation of this Indonesian through flow water coming back towards Australia. So we wanted to look more carefully at the Leeuwin current system. So we were aware of this strong southward flow and a northward flow at deeper levels, but we didn't have a sense of the amount of water being carried and how those surface and deeper layers were interacting and potentially exchanging water. So we began a study using new observations from Argo that were built into an atlas by CSIRO called CARS, the CSIRO Atlas of Regional Seas, and new high-resolution models that allow us to look close to the boundary, which is a very difficult place for observation and large-scale models to work with. So what we see on the left then are some west to east transects across the Leeuwin current at different latitudes. So from 22 south in the north down to 34 south. And what's plotted there is the north-south current. So the blue colours indicate a southward flow and the red colour indicates a northward flow, and this grey line is the ocean bottom as we come from the coast of Australia down to the deep ocean. So then we wanted to see the spatial patterns of these currents. So we've added up the amount of water being carried in the southward flow above 200 metres all the way down the coast and offshore. And so in the right panel, we have a plan view looking down on the Leeuwin current, and the blue colour indicates how much volume is being carried by each column of water in that map. And you can see some southward flows coming into the north of the Leeuwin current and intensity increasing, and then the current moves eastward, south of Australia. You can also see with the vectors, so the colour only indicates the north-south movement of water, but the arrows show you the full vector currents, and you can see the exchanges coming in the eastward flows from offshore. Then we can also look at the Leeuwin undercurrent, which is this northward red colour in the left-hand side that extends between 200 metres and 900 metres depth. So a similar map for the Leeuwin undercurrent shows northward movement of water that starts off relatively weak and increases northward and then moves offshore. So that's the horizontal circulation, and we were able to put these together to look at the vertical exchange between these two layers. So where we have a convergence of water in the surface, that will lead to downwelling movement of water to the deeper layers, and if the surface layer has some divergent flow, then that will lead to upwelling from below. And so that leads us to looking at this downwelling pattern along Western Australia. And I'll try to explain this figure clearly. So what we're looking at is the amount of volume transport in each of the incoming eastward flows in the top dashed line, the southward Leeuwin current in the solid black line, and the downwelling movement or the exchange between the surface flows and the Leeuwin undercurrent. And we've done it as a sum from the northern end of the Leeuwin current moving southward. So we need to do that because of the to allow us to estimate this downwelling part. And what we see is that the downwelling is a very steady increase as we move southward. So it means that there's not a lot of impact on this downwelling by eddy motions, which strongly affect the horizontal currents, because you see these strong upward and downward movements. But the total downwelling adds up to about 3.5 sverdrups along this west coast of Australia. And this schematic summarises those circulations. So the red arrows indicate the Leeuwin current depths, which is from 0 to 200 metres, and we see a weak inflow in the north, and then the Leeuwin current moving down the coast of Western Australia and turning to head east. And the eastward flows are represented here as these incoming red arrows, and the total amount of water coming in from the Indian Ocean is 4.7 sverdrups. And I should have said earlier that 1 sverdrup is 1 million cubic metres per second of water, so quite large volumes. There's a strong conversion of the incoming waters into a downwelling that feeds the Leeuwin undercurrent depths. So almost all of the water that comes in from the Indian Ocean is downwelled into the Leeuwin undercurrent depths, shown in the white arrows there, that then moves northward and leaves the coast between 25 and 20 degrees south. So that allows a pathway of Indian Ocean surface waters to sink down below the Leeuwin current into depths at least as deep as 300 metres and possibly deeper, and then be carried northward and move offshore. So that's one window into deeper levels of the ocean. And here's a bit of a summary slide. So we have 90% of the inflow to the Leeuwin current coming from the west, and a large part of that is downwelling to feed the Leeuwin undercurrent, so that the undercurrent gains most of its volume from this downwelling and moves northward and offshore. So then we want to turn to think about the circulation along the southern coast of Australia. And this is called, well, this is now called the South Australian Current System. So a lot of work has been done on individual currents south of Australia, but not really thinking about the circulation as a complete system. And so Earl Duran, who's a student at University of New South Wales, has done this very nice piece of work that's contributing to Project 5.7 to try to look at this system as a complete system and not just individual currents separated by longitude. So what we have then are these three components of the South Australian current system. There are the eastward flowing shelf break currents shown in blue. So these sit really tight into the coast where the water is still not very deep, so above 200 metres. And they move, they consist of the Leeuwin current extension that's come from Western Australia, and that flows into the South Australian current system, and then all the way south to join the Leeuwin current along the west coast of Australia. And beneath that and offshore is the Flinders current shown in red, and that begins south of Tasmania with a quite strong flow that heads due west, and not very much flow actually starts to move northward. But as the Flinders current moves northward and westward, it picks up volume and becomes stronger as it moves to the west. And the orange arrows show flows coming from the Southern Ocean over a depth range of 2,000 metres that feed into that circulation. And in the same way that we looked at a slice of the Leeuwin current, this is now a vertical slice on the right-hand side of the South Australian current system, and it extends to 2,000 metres depth. And you can see the shelf break currents moving eastward above 250 metres, and offshore and beneath the shelf break currents are this very large flow of the Flinders current. And the schematic on the right tries to illustrate the different exchanges that we found. So there are very shallow coastal currents up on the shelf. There's the shelf break currents, and there are some horizontal exchanges between those. There are vertical exchanges between the shallow shelf break currents and the Flinders current beneath, and then strong onshore flows that contribute to the offshore part of the Flinders current. So we have a schematic similar to what we did for the Leeuwin current. That's a little more complicated, but the main points are that the shelf break currents are actually relatively weak. We've only got less than 1 spurdrip of volume transport moving all the way around the coastline, but there's downwelling feeding into the Flinders current, and the offshore arrow, so orange indicates shallow layers and the white indicates the subsurface layers. So the Flinders current moving westward is both a surface and a deep current. It extends down to 2,000 metres, and it receives water from the south, and it builds in volume as it moves towards the west. So it's 2 spurdrips in the middle of the Great Australian Bight, and then by the time it passes Cape Leeuwin, it's up to 12 spurdrips. So this is depicting a movement of water from the Southern Ocean carrying subantarctic mode water and Antarctic intermediate water northward into a circulation or a boundary current that's very efficient at carrying those waters along the south coast of Australia and then up into the Leeuwin current, Leeuwin undercurrent. So let's put that together. So there's onshore flow and downwelling across the western and southern coastlines that together are contributing to a pathway of water masses to move into the deeper parts of the ocean. So as we saw on the west coast of Australia, there's a downwelling of large amounts of water from the Leeuwin current into the northward flowing Leeuwin undercurrent that then moves offshore into the Indian Ocean. And then south of Australia, there are deep onshore flows moving northward that are carrying subantarctic mode water and Antarctic intermediate water. And these are then entering the Flinders Current, moving westward and then northward in the Leeuwin undercurrent and offshore. So you might say, well, how do we know there are subantarctic mode waters and Antarctic intermediate waters here? And that comes through looking at the water properties. So this looks a little complicated, but it's not so bad if we take it one bit at a time. So in the top left two panels, we have a picture of ocean temperature. And the way these are arranged is that we have a vertical slice from 0 to 2,000 metres. And then if we start at the right edge of the second panel, we're moving from the middle of the Great Australian Bight at 132 east, west along the coast of southern Australia. And then we're turning around Cape Leeuwin and moving northward from 35 south up to north of 20 degrees south. And we're following this boundary current system. And so we're taking one, so we're looking at the change in temperature along this boundary current. So the initial things to notice are that the waters are cooler south of Australia, and then as we move west and northward, they become much warmer, particularly up in the tropics. Then if we move to the two bottom panels, we're looking at salinity. And again, we have the same orientation, moving from Great Australian Bight westward to Western Australia and then north up the west coast of Australia. And the salinity shows very beautifully the minimum or the very fresh waters of the Antarctic intermediate water, moving to the west and then northward and becoming weaker as they mix with other waters in the Indian Ocean. And in the upper ocean, we see higher salinities in the south, and the surface waters become fresher as we move north and start to feel the Indonesian through-flow waters in the north. The subantarctic mode water is very well identified by what we call potential vorticity, which is showing where the waters are very well mixed. So there's very weak vertical density gradients, and that shows up as a minimum in potential vorticity moving westward and then northward. And the other nice feature of subantarctic mode water is that it has a very high oxygen concentration, and we see those high patterns of dissolved oxygen again moving northward. So there's a very clear water mass indication of this pathway for these waters to move along Australia's boundary currents. So I'll just finish with a bit of a view of where we plan to go from here in terms of the science. And the first thing that we're working on is to quantify the volume and property transports within the subantarctic mode water and Antarctic intermediate water layers through this boundary current system. We want to look beyond Australia's coastline and identify the pathway that Leeuwin undercurrent outflow takes into the tropical Indian Ocean. So we've seen that there are strong changes in subantarctic mode water properties in the Southern Ocean, and it may be that their modification is being felt in the Indian Ocean as a change in the rate that the ocean is warming there. We'd like to estimate the contribution to the change in heat content then in the Indian Ocean. And some parallel work that's being led by Sorab, a student with us, is to document the regional distribution of ocean heat content change, and to be able to separate out the changes that are due to what we call known modes of variability. And that would include things like El Nino and the Indian Ocean dipole and the southern annular mode. So we can tease apart the changes in heat content that are due to these different climate modes, and then see more clearly the part that is due to the human-induced climate change. And then a very key element of Project 5.7 is to continue to support ocean observations and developments in numerical models that allow us to investigate these pathways of ocean heat uptake and circulation in the oceans. So that's where to from here in the sense of our science, but there's also where to from here in the sense of our place in society and on this planet. And I think where to from here can only be a transition to zero emissions of greenhouse gases as quickly as we can, because there's more and more evidence that the cost of continued warming is just too high. And this is a figure produced by the Global Carbon Budget, the Global Carbon Project, and they're researchers in the Earth Systems Climate Change Hub who are making big contributions to this effort. But what it's showing is that the time series of fossil carbon dioxide emissions is continuing to increase. There was a little plateau, which I believe was the global financial crisis, but there's acceleration again. This bottom panel here, which is labelled temperature, has two pathways, and one indicates less than 1.5 degrees C and one's greater than 2 degrees C. And the IPCC looked into what would it mean in terms of the consequences of global warming if we were to allow global average temperatures to exceed 2 degrees C versus if we were to be able to keep them to less than 1.5 degrees C. And the conclusions from that report was that there are massive changes in every half degree of warming and impacting many different areas of the climate system, and they recommend that emissions need to rapidly decrease to zero to limit climate change and its impacts. And the curve at the top labelled emissions suggests different pathways for emissions that will allow us to get to global average temperatures of less than 1.5 degrees warmer versus 2 degrees. And you can see that there are some changes needed soon. So I'll finish there and welcome any questions.
Thanks, Helen. Thanks for a really informative presentation. Just a reminder to everyone to pop your questions in the chat box now so that we can ask Helen as we go. We've got a couple to begin with. So Helen, Ulrich asks or says, thanks for the excellent presentation. With the warming of surface waters, the particularly large warming of the Southern Ocean, as well as the connectivity of the currents, what do you think are going to be the consequences for deeper waters?
I think that we've seen already the consequences for deeper waters in terms of warming, and that warming will continue. The other aspect of these deep pathways is that carbon dioxide from the surface of the ocean is also being taken down into the deep ocean, and that has the effect of increasing the acidity of the waters there. So that has an enormous impact for creatures that have a carbonate shell, and so it results in a displacement of many of the species to places where they can exist more comfortably, either due to the temperature or due to the acidity of the ocean. So there are quite a lot of work being done to map the movement of species, and to a point they can find new environments, but at some point the hospitable parts of the ocean will disappear if we allow warming to continue.
Fabulous, thanks. We've got another question from Sarah, who asks, can you elaborate on why there is such a high level of warming in the North Atlantic? And then in commas, although it looked like second slide showed cooler, question mark.
That's right. Those two slides were from different time periods. So the first one was the warming or change in ocean heat content since the 1970s till 2010. And the warming in the North Atlantic is really indicating that pathway of the North Atlantic deep water. So in that region, the surface waters become very cold in the northern North Atlantic, in the Labrador Sea and the Norwegian Sea, and they become very cold and so very dense, and that enables them to sink deeply and then move southward. So they're picking up, while they're at the surface, those waters are picking up the warming of the atmosphere, and then they carry that warmer surface signature. Even though they're cooling and becoming more dense, they carry that warming signature down into the deep ocean. And so the North Atlantic has a strong warming signature in that early time, but a surprise during the more recent decades, since 2005, when we had Argo observations, is that the North Atlantic is actually not warming and even cooling. But that's over a very short time window, and what we're discovering through Sorab's work during his PhD is that cooling is related to the ocean moving heat around internally, and doesn't mean that the warming due to increasing greenhouse gases has stopped in the North Atlantic. So that's part of the reason we need to tease apart the different contributions of the climate modes versus the human-induced warming, so that we can clearly understand these sometimes not easily interpreted patterns.
Okay, fabulous. We have a question from Ali, who asks, like the Antarctic bottom water, are there any particular locations longitudinally where the subantarctic mode water and the Antarctic intermediate water predominantly form?
Yes, in fact, so the subantarctic mode water forms where we have very deep mixed layers north of the Antarctic circumpolar current. And it happens that south of Australia is one of the very important places for forming subantarctic mode water. So we have a lot of subantarctic mode water south of Australia that moves into the Indian Ocean. It turns out that the Antarctic intermediate water is more formed to our east in the southeast Pacific. So that's a denser water, and the conditions are more suited to that water mass formation in that Eastern Pacific region.
Question from Paul, who asks, any thoughts about the relationship between the Indian Ocean dipole and the Leeuwin current and down current?
Yes, the Indian Ocean dipole is a very important mechanism in the Indian Ocean, and it sort of works in concert with the El Nino Southern Oscillation phenomenon to some extent. It is possible for the Indian Ocean dipole to exist by itself, but we often see that the Leeuwin current system is affected by both. So, for example, the El Nino, when we have an El Nino as opposed to a La Nina, we see a much weaker Leeuwin current, and then if we have a La Nina, we get a much stronger Leeuwin current. So there are also effects that the Indian Ocean dipole will have, but I'm not so clear on what they are in terms of variability in the Leeuwin current system.
Okay, thanks for that. And you also talked about the Argo measurements and how they could measure down to, I think you said, 2,000 metres down. Are there any plans for measuring below that, or any other equipment or technology that's on the go to measure below that depth?
Yes, there are. So Argo is actually, the groups who make Argo floats have actually been working hard to develop a system that will withstand the really extreme pressures of the deep ocean. And so there are Argo floats that can profile from the surface down to 6,000 metres depth. And these are obviously a lot more expensive than the standard Argo floats. So there's a bit of a challenge to expand our network to be able to cover that 2,000 to 6,000 metre gap. But the technology is there. It's really just a question of increasing the support for this for this observing system so that we can put out more deep ocean profiling floats. So the Project 5.7 team have some deep Argo floats down in the Southern Ocean, looking at Antarctic bottom water pathways and changes. So yes, this is coming, but it needs some support.
Okay, fabulous. And probably just one last question. We also we often hear about eddies and wind and the role of that in sort of mixing the oceans. Does that play an important role in absorbing that carbon dioxide from the atmosphere into the ocean?
Yes, it does. I've been involved in a project that's been looking at eddies in the Southern Ocean and how they affect the uptake of carbon dioxide, and they can act to release carbon dioxide to the atmosphere, and so that is still work in progress. But I think the eddy variability is something that hasn't been considered very closely as far as how that will affect the continuing uptake of CO2 by the ocean. So that again is work in progress.
Okay, thanks. All right, well, I think I've gotten through all the questions that you've got. So you've got one last minute, anyone, if you want to ask a last question. Otherwise, that sort of brings us to the end of the webinar. So thank you, Helen, for a really great presentation. And also thank you to all the attendees for taking time out of your busy day to attend. I'd just like to make a few notes quickly that a recording of today's webinar will be available by the end of the week on the Hub's webinar website. So if you want to pass that on to anyone or revisit anything that you've heard today, please check it out. And also a quick plug for next month's webinar. The November Earth Systems and Climate Change Science webinar will be provided by Simon Marsland from the CSIRO on Wednesday the 13th of November. And Simon will be presenting on the Access Climate Model Submissions to the World Climate Research Programme's Coupled Model Comparison Project, or CMIC6, which is our contribution to the international model efforts underpinning the forthcoming assessments of the future climate in the IPCC 6th Assessment Report. So the usual email will be going out to everyone closer to the date. But if you have any last questions or any questions about the Hub, please do get in touch. On the screen there, you've got some ways to get in touch with the Hub. We'd love to answer any questions that we can. And otherwise, thank you for attending again, and we look forward to seeing you at the next Earth Systems and Climate Change Hub webinar. Thank you.